A DDS VFO stands for Direct Digital Synthesis Variable Frequency Oscillator. It is an electronic system used in radio transceivers to generate a highly stable, adjustable radio frequency signal using digital signal processing rather than traditional analog tuned circuits like coils and capacitors. In modern homebrew and commercial amateur radio rigs, it serves as the tuning dial generating the local oscillator signal required for mixing down received signals or mixing up transmitted signals. Though I have been mentioning the VFO in my ECBTEX build as a DDS VFO, in the strict sense it is not. Technically, it uses a PLL, phase locked loop clock generator, specifically the Silicon Labs SI5351A integrated circuit. Unlike a legacy analog VFO which we used to have in our popular VWN QRP that changes frequency by physically altering capacitance or inductance, a DDS generates a voltage waveform digitally from scratch using a fixed frequency reference clock. The internal architecture consists of four primary building blocks. One, phase accumulator. This is a digital counter that increments its value at every tick of the master reference clock. The amount by which it increments is determined by a digital frequency tuning word sent from an external microcontroller. Larger increments means the counter wraps around faster, resulting in a higher output frequency. 2. Phase to amplitude converter, sine lookup table. The digital output of the phase accumulator represents the instantaneous phase of the wave. This phase value acts as an address for a digital read-only memory matrix that stores the corresponding digital amplitude values of a pure sine wave. 3. Digital to analog converter. The digital amplitude values from the lookup table are fed into a high-speed digital to analog converter, converting those numbers into a stepped analog staircase voltage waveform. 4. Low pass filter. The output of the digital to analog converter contains high frequency sampling artifacts and imaging products, aliasing. A reconstruction low pass filter smooths out the staircase steps, leaving a clean analog sine wave at the desired frequency. Now a little bit of maths for those who are technically minded. The output frequency F out of a DDS system is governed precisely by the following equation. F out is equal to M into F clock all divided by 2 to the power of n. M is the digital frequency tuning word, the phase increment value. F clock is the frequency of the master reference crystal clock. N is the bit resolution of the phase accumulator, typically 24 to 32 bits. Because N is usually quite large, the tuning resolution, step size, can be incredibly small, often less than 1 Hz. That's what we call sub-Hertz resolution. Key advantages of a DDS VFO. Rock solid frequency stability. Traditional analog VFOs are prone to frequency drift caused by temperature changes affecting the inductors and capacitors. I have experienced this very much during my initial era of homebrewing. A DDS VFO inherits its stability directly from its master crystal oscillator, often a temperature compensated crystal oscillator or TCXO, meaning it virtually never drifts. Sub-Hertz tuning resolution. You can tune in increments of 1 Hz, 10 Hz or even fractions of a Hertz, allowing for ultra precise tuning of single sideband or narrowband digital modes. Microcontroller integration. Because the frequency is controlled by a digital word, it interfaces seamlessly with microcontrollers. This easily unlocks features like digital dual VFOs, split operation, programmable memory channels, and electronic frequency displays. Ultra-fast switching. A DDS can jump from one frequency to an entirely different band almost instantaneously, making it highly agile. A common distinction, DDS versus PLL, as in SI5351A. In modern radio circuitry, you will often encounter two types of digital oscillators. True DDS, example AD9850, AD's analog devices, AD9851, AD9951, etc., generates the waveform entirely via digital synthesis as described above. They produce native sine waves but can suffer from low-level spurs or spurious emissions at certain frequencies, requiring robust low-pass filtering. Phase-locked loop or clock generators like SI5351A, though often colloquially grouped with digital VFOs, the SI5351A is actually a hardware PLL clock generator. It generates frequencies by multiplying and dividing a reference clock using fractional multipliers or dividers, producing a square wave rather than a sine wave. This is my question: does ECBTX have a true DDS VFO or PLL? You know that I have been homebrewing ECBTX. The short answer is no. The ECBTX does not use a true DDS VFO. Technically, it uses a phase-locked loop clock generator, specifically the Silicon Labs SI5351A integrated circuit. Despite its technical architecture, it is very common to hear homebrewers, video tutorials, and kit documentation colloquially refer to the Arduino controller on the ECBTX as a DDS or DDS VFO. In amateur radio community, DDS has often become an inaccurate shorthand for any digital drift-free VFO system. I was also using the same term so far. How the ECBTX VFO architecture actually works. The digital tuning heart of the ECBTX is the Arduino daughter board, which I had shown earlier, or a local variant of it, which consists of the brain, an Atmega 328P microcontroller, typically via an Arduino Nano form factor. My ECBTX has Arduino Nano. The synthesizer, SI5351A clock generator chip controlled by the Arduino via a 2-wire I2C interface, SDA and SCL lines. Instead of digitally constructing a waveform from a phase table like a true DDS chip such as the AD9850 or AD9951, the SI5351A uses an internal crystal oscillator reference to drive two internal fractional and phase-locked loops, PLLs. High-resolution multi-synth dividers then step down the PLL frequencies to generate the exact target outputs. In the standard ECBTX firmware configuration, clock 0 is programmed to output the VFO signal, which shifts as you turn the rotary encoder. Clock 1 is programmed to output the fixed BFO, beat frequency oscillator signal, usually sitting right around 10 MHz mark to match the transceiver's intermediate frequency IF crystal. Understanding what is actually coming out of the Arduino board matters when you are building, testing or troubleshooting the rig. Output waveform. It is square wave form in ECBTX VFO. True DDS, it is sine wave. Harmonics. ECBTX, it's rich in odd harmonics, 3F, 5F, 7F, which requires robust band pass filtering downstream in the mixer exciter stages. In true DDS, it is relatively clean fundamental signal, though susceptible to low-level spurious emissions or spurs. Current consumption very low, typically under 30 milliampere for EC-BTEX VFO. It is higher, often running warm to test the especially older chips like AD9850 in case of true DDS. Then independent clocks, up to 3 independent RF outputs from a single tiny SI53518 chip, allowing to provide both VFO and BFO, bit frequency oscillator, simultaneously in EC-BTEX. While true DDS, only one fundamental RF output per module is possible. Because the SI53518 generates a square wave, checking the VFO or BFO output line directly with a simple RF probe or oscilloscope will show a digital signal rather than the smooth analog sine wave. The conversion to a clean operating frequency happens down the line as it runs through the trifilar transformers, the diode ring mixer, and the transceiver's tuned band pass filters.